Consider the function y equals x squared ln x. We want the domain and x-intercepts. Well, as far as the domain is concerned, the ln will have the big effect on that. So we must have only positive values of x. That means that the intercepts that you'd think would come from x squared, i.e. x is 0, doesn't exist. So ln 1 is 0, so the x-intercept can only be 1, 0. So we now want the exact coordinates of any stationary points. Well, we can see that's a product. So u is x squared, v is ln x. du dx would be 2x, dv dx would be 1 over x. So dy dx is going to be v du dx plus u dv dx. So that's just going to be x. So we have x 2 ln x plus 1. If we want dy dx to be 0, then we have x 2 ln x plus 1 equals 0. Well, x equals 0 is clearly one of those, but we can't have that because we know the domain. So we have 2 ln x plus 1 equals 0. That gives me that ln x is negative half. So x would be e to the negative half. The corresponding y coordinate would be the square of that, which is e to the negative 1, times ln e to the negative half, which is just going to give us negative half. So that gives me negative half e to the negative 1, or negative 1 over 2e. So the coordinates of the only stationary point, e to the negative half, negative 1 over 2e. We now want to use the second derivative test to determine the nature of the stationary points. So what we need to do is differentiate again. So d2y dx squared, well, this is going to be a product v du dx, so that's going to be 2 ln x plus u dv dx, so that's just going to give me 2, and then that's going to give me 1. So it's going to be 2 ln x plus 3. And we want d2y dx squared, given that x is e to the negative half. So that's 2 ln e to the negative half plus 3. So negative half comes down, multiplies the 2, gives us negative 1. Ln e, of course, is 1. So it's negative 1 plus 3, which is 2. And that's positive, and that would imply that we have a minimum